I'm going to be talking about colliding plane gravitational waves. Here is the plan of the talk, just one-page introduction, and then the question that had arisen on the reality of gravitational waves, the formalism that I developed with some people to be able to see relativity effects better, then the colliding impulsive plane gravitational waves, then colliding sandwich plane gravitational waves, then the generalization to unequal strength plane gravitational waves, a conclusion, and an epilogue. The explicit prediction of the existence of gravitational waves was made in 1916, but no one believed at the time that they could ever be actually detected. As such, no one took their existence too seriously. An objection was raised about their physical reality in principle, as the stress energy tensor is zero for the vacuum. Now, if that is zero, that seems that they cannot carry any energy. It be zero. And then how can you have waves if they can't, if they're not carrying energy, then what are they? There were two exact gravitational wave solutions. Remember, these are nonlinear differential equations, the Einstein equations, so exact solutions are few and far to come by. There were two exact gravitational wave solutions for cylindrical waves and then for plane waves. Surprisingly, the cylindrical waves came first and the plane waves considerably later. The problem of reality arises as energy is not well defined in GR because of the lack of time translational invariance. A mass in the field of a massive object acquires energy from the curvature of the space-time. Put the Earth near the sun and, well, it starts moving, and that violates energy conservation, apparently. So then we can see there's a problem. Similarly, with the expanding universe, every photon loses energy. So the energy loss of the photon doesn't really seem to make sense because in classical terms it doesn't. In 1957, Weber and Wheeler calculated the momentum imparted to test particles in the exact solution of cylindrical gravitational waves and proved that they really exist in that sense. Later, Ehlers and Kuhn repeated the process for the exact solution for plane gravitational waves. Though Einstein expressed the force of gravitation to bend paths as the curvature of space-time, a classical description ascribing the bending to a force may often be desirable. To retain the full GR result, what one is talking of doing is that you flatten the space-time out so that the jury six look like straight lines, and now ask for a force that bends the path to exactly match the GR path. This formalism was called the pseudo-Newtonian formalism, and that had the GR force written as a psi n force, and the GR potential as a psi n potential. The psi n force was based on an operational definition by using the tidal force given by the geodesic deviation for an accelerometer represented by a space-like vector. Lee transported along the unit time-like vector t. I'll just be mentioning about the Lee transport rather than parallel transport. So this would give the tidal acceleration A as the curvature tensor dot the time-like Killing vector times the separation vector times the time-like Killing vector. Because it's a fourth rank tensor, this will become a first rank vector by A equal to grad T F would be then that F is the force. And so in Minkowski space, it should be 0. This gave the correct behavior for the Schwarzschild metric and provides new insights for the Kerr metric, including an interpretation of Carter's fourth invariant of the motion. Here is this thing that I was describing. Here are two of a family of GD6, gamma I and gamma J, having unit tangent vectors, T, and connected by a separation vector P, acting on a point P, it takes you to Q from gamma I to gamma J. Later acting on R, it will take you to S. Now Lee transport would take us from T, would take T onto U. But if I were to do the parallel transport, you'd see that the vector here and this, keeping them parallel and the same size, as it were, it would take T up to here, not up to there. This difference is what we're talking about from the Lee transport to the parallel transport. And so this is what one would measure by the acceleration, the tidal force. The psi formalism cannot be used in time-varying spacetimes as the zero of the accelerometer changes with time. So an extended psi formalism was developed. The old one just was fully constructed static space-time, and we needed that it should not be just a static or stay even stationary, but it should be genuinely time-varying. And that was then the E-psi formalism. Weber and Wheeler used second-order approximate geodesic equations of cylindrical gravitational waves for the momentum to test particles. The E-psi formalism gives a closed-form expression for the momentum, which yields the Weber-Wheeler result as the second-order approximation. Now, coming to colliding plane gravitational waves, when I joined Roger Penrose for the PhD in 1968, he had asked Khurshid Alam Khan of Karachi University, who was doing his PhD there, to solve the Einstein field equations for colliding impulsive plane gravitational waves that was based on his topological cut and paste construction of an impulsive shock plane wave. Khurshid discovered a new exact solution of the field equations in the process. Now, He was unable to derive the solution of the 10 nonlinear coupled partial differential equations for 10 functions of 4 variables. It's a horrendous task. Even with the symmetry of plane waves, there's no time symmetry, so it was still pretty bad. So he just wrote it down. Couldn't derive it. I asked him how, and he didn't know. He said, I don't know. But you check it, it's correct, which it was. He couldn't have stolen it from somewhere because nobody had it before. The solution is given in terms of the retarded and advanced times, which are the same linear which are potential advanced and retarded, retarded and advanced time. We're taking c equal to 1, the speed of light. The functions for all 4 regions were expressed as a single formula by using the theta functions, the step function. The procedure used automatically gave the shock waves to be of equal strength. In fact, there was no measure of the strength of the shock waves given. I'm just giving this for completeness. I don't expect people to follow these. There are these 3 separate functions that we're talking about, 2 here, third one there. And then these variables have the u and then the theta v and then the theta for q. And that's how this is. The theta was put in by me. One problem was that the coordinates should be dimensional, but in the metric they did not appear to be so. When written this way, u squared plus v squared equal to 1, there are no units. The Penrose colliding impulsive shock plane gravitational waves are these, and the 4 regions are put into one formula using the theta function. Of course, then you have a step function in the metric tensor, and then you start differentiating the metric tensor, you will indeed immediately end up with these delta functions here. So those are the impulsive waves. Now that would be the first derivative. The second derivative would give a derivative of that, and then you use the formula for the derivative of function in terms of the function. And so that would give us the final results for the metric. Now, these are the Penrose equations that I'm talking about. Hahn presented a seminar on the solution in 1969. This was in London, and there's an enormous community there. Everybody would get together at one place. So he presented it over there. As it happens, he presented it at King's College itself, where Peter Szekres worked. And Peter was present. I saw him there, and this was for the colliding plane sandwich gravitational waves. Peter publishes a paper before Penrose and Hahn do. Why was it that he got the opportunity to publish before? Because Khan was busy writing up his thesis so that he could get back to Karachi. He kept on giving his reason as his mother being ill, so he had to go back. And he never did the analysis that Penrose asked for. And so finally, Penrose had to write the paper himself. Uh, and that delay meant that Peter Szekres got an opportunity to squeeze in his paper first. I'll have comments on that later as well. As the KP gravitational waves are shock waves, a constant momentum would be imparted by them in regions 2 and 3. This back here, you see that region 1 is flat, it's before either gravitational wave goes by. Here, one of the gravitational waves is gone by and not the other one. Here, the other one is gone by and not that one. And here, they both crossed over, and so you've got the collision. So this is the, now there's a curvature singularity at u squared plus v squared equal to 1. And there are topological singularities at v equal to 1 and u equal to 1. This had not been so clear that it was topological. The question had been debated, but Sharif and Qadir and I studied the momentum as well, but we also managed to show that that's a topological singularity indeed. There's a problem of working the force out because the coordinates are dimensionless. So why do we need the dimensions, put them back in? Introduce a dimensional constant t, that's a time, giving the end of the KP universe. So remember C equal to 1, so distance and time have the same units, and so U equal to T minus Z over capital T, and V equal to T plus Z over capital T. And then we can define distance and an angle, the distance being associated with the time and the angle as just tan inverse V over U. This enables us also to depict the results of the way the E psi force varies with theta. This is that small theta is the angle, not the step function. And here is the graphical representation of the psi force reaching a maximum and then going down to zero either side, and then to maximum. Remember that these are the KP gravitational waves still I'm talking about. And then we've tabulated here the force as it turns out. There's the maximum, for example, at this theta, this value, comes at this place. So you can see that at different angles, you'll get something very clearly there. Now, the Peter-Szekres colliding sandwich gravitational waves. These are much more complicated than given in the PSN and PSJ way, actually. The errors are given in detail in this paper of ours. This is what it should look like. So there's region 1. The sandwich here is going, and the sandwich here is going, The sandwich here is now, that's beyond the sandwich, so it's passed. And this is also beyond the sandwich, so it's passed. And here, the two sandwiches have collided and made, I suppose, a club sandwich. So anyhow, uh, that is what should have been. What Szekres had got was this. And he had these going out endlessly. And there wasn't anything like that there and that there. Notice that there's no limit to the region beyond 2 and 3, and 4 for that matter in this. You could go over here. Now this looks, it should be a curvature singularity, so there should be nothing beyond, but there is something beyond between here and here, as far as Peter Szekres's diagram and all his entire discussion is concerned. These are not defined beyond u plus v equal to 4, u4 to v4 equal to 1. The distance and angle are more complicated because instead of being quadratic, it's gone quartic, and then the theta is this tan inverse t over z. Though the theta could have been given for the Kp waves, it was not needed there as it was the usual one. Here, the metric can be written in this way. With region 1 given with these things, and here I don't expect you to follow all this formula, but there it is for completeness. And so here we have I don't know why this thing comes in between here. Well, now here we have the U and M coming in, and this is the metric for the collision region. Doomsday, that is where T is, the end of the universe, is, as before, a T. The question is, what is this T? How can we identify it for an actual gravitational wave as opposed to just a number in a solution? What precisely does it depend upon? I don't know how to get rid of this extra thing here. I don't know, this is interfering anyhow. So this seems to be an inverse measure of how strong the waves are. The larger the T, the stronger, the weaker the wave, the smaller the T, the stronger the waves. So what happened now? Yes. So this is the force for completeness. I won't belabor it. I was always bothered by what the strength of a gravitational wave is. The literature on exact solutions does not clarify this point, and we cannot look to the energy of gravitational waves, as I explained earlier. The exact solutions use a normalized function in units where the strength was not included. So, for this simple pendulum, it is clear enough. What does the strength indicate? The energy depends on how hard it is hit to start the oscillation, and on the energy due to the number of oscillations per unit time, the frequency. So there are two things, the amplitude and the frequency, which determine it. That's well known. This problem was not crucial for the solution for one gravitational wave and could generally be ignored. In some sense, the strength was given by the momentum imparted to test particles by the gravitational waves, and in some sense, by the slowing down of the pulsars, binary pulsars, and in some ways by the strain seen in the length increase of a bar or the arm of an interferometer. However, it was not clear how to separate off the two parts. The matter could not, it really is bothering me. I want to hide that and I can't anyhow. Well, this is when however, it is not clear how to separate these when dealing with a single solution, as the solutions were, what was it? I just can't remove this thing.
What seems to be bothering you, Qadir sir?
मुझे क्योंकि खुद भी नहीं फिर वहां से पढ़ा जाता.
I think it's talking about floating. जो zoom controls show रहे होते हैं when you're sharing the screen.
This video panel. There we are. So this was what I was saying. It was not clear how to separate off the two parts. The matter could not be shelved, however, when dealing with a single exact solution for two gravitational waves. In the solution, they were assumed to be of the same strength. What would happen if the colliding gravitational waves are of different strengths? To answer this, we need to identify how their strengths are expressed in the metrics. Clearly, the momentum imparted to test particles will no longer cancel at the instant of impact. We need to identify the parameters giving the strength using this criterion. We use the WW method and the E-sign formalism for this purpose. It was found that the strength varies as t to the -4. So the inverse Ts, fourth power. For different strengths, this is for the Kp, for the PS waves. For different strengths, we use different doomsdays for the two waves, T2 and T3. The vacuum solution metric comes out this way, which are then given in the diagram on the next slide. And here is the functions given for completeness. Now you see that this is no longer symmetric because of the unequal strengths. I've taken here, I shouldn't deny, with a 4/5 T3 to T2. So there's 5 times, and this 4 times of a common width. This way you get the distortion. And so here we have the larger T is, the weaker is the gravitational wave with that fourth power. Here T2 greater than T3, so the left wave is stronger. In region 6, both U2 and V3 are used. You see over here. Notice that if we take T3 equal to T2, the diagram will revert to symmetric, and it would be a corrected version of the erroneous diagram that appeared in the original paper. That is what Szekres would have got if he had derived this formula for himself, or at least understood it, and not simply stolen the idea from Khan's seminar. We first dealt with the Szekres gravitational waves. How about the KP waves? Well, all we have to do is take the limit as the thicknesses of the sandwiches go to zero so that they become impulsive, and the intensity is correspondingly increased so that the net result is that doomsday remains the same. The T2 or T3 are the same. This will obviously give the KP gravitational waves. And so here we got the generalized KP gravitational waves. The formula was fairly reasonable and gave the answer. Again, the left wave is stronger, 1.25 times. In region 6, both U2 and V3 are used. Region 4, that shouldn't be 6. It's this one. And this is wrong. There are now only 4 regions. Penrose pointed out that the unequal strength could be obtained by a Lorentz transformation in the direction of motion. That would change the strength, apparently. And so then he asked, is that this could have been done in any case, but perhaps you had something deeper in mind. So we tried to look for the something deeper. The strength would correspond to a frequency by the Lorentz transformation argument. So that would just come out as compressing the time and expanding the time. So you're going to get 2 different frequencies, apparently, and that would be what is brought it about. However, this strength does not include the amplitude, which would also be used in the derivation. How would that be obtained for gravitational waves? Well, one is used to a field without a source in EMT. It appears inconsistent for GR as it leads to energy momentum non-conservation. To overcome this problem, right in the early days of GR, it was proposed that there should be a pseudo-tensor, tau mu nu, which would be that you take the gravitational theory as full, linearize it, get the linear equations with the nonlinear assumed to be small, lump all the nonlinear parts together, take them to the right-hand side as a source. That would be then the pseudo tensor. For gravitational waves, this procedure gives a non-homogeneous wave equation with the T mu nu as a source there. For a single plane gravitational wave, you get here. In region 2 of the PS solution, we could use this formula as it is with U2, and in region 3, simply replace U by V3. Hence, both waves have amplitudes depending on the curvature of the space-time, at any space-time location after it is produced, which would be different. In region 6, the pseudo-tensor was given by over here. Thus, the frequency and the amplitude seem to have been fully interpreted. Now, the conclusion. The first exact gravitational wave, Einstein and Rosen in 1937. Second, Bondi, Pirani, Troutman. Third, just written down, called Shahid Khan. Just wrote it down with the Khan Penrose colliding impulsive plane waves of equal strengths. Inspired by their solution, Szekres constructed the colliding sandwich plane waves of equal strength and gave that. We had stolen the idea. We managed to determine a parameter which gives the strength and used it to obtain a solution of the unequal strength wave. By taking limits, we obtained from the KP, from the PS, the original KP waves of unequal strength. And then by taking them equal, we recovered the original KP solution. As such, we have a derivation of the KP solution for the first time. Khan had just written it down. Here we have a derivation. But I have a problem with that. KP wrote down the solution without deriving it. PS stole from KP. We generalized the PS solution and used it to generalize the KP solution, and then reverted to equal strengths, and now we claim to have derived the original solution. But is this not circular? I seem to have gone round in a circle. The derivation still doesn't seem to have come from anywhere. Where on earth did the original solution come from? Khan had just written it down while we were deriving it, but we've derived it by using something that was used by something going back to just using the KP. I had confronted Peter Szekres on this matter when I met him on a visit to London in 1978. Now, he flatly denied knowing of the paper published after his own at an earlier time. I pointed out that he had been at a seminar in King's at which Khan had presented it and told him where he had sat at the time, but he maintained his stout denial. You know, the Goebbels way, just stout denial. So was he sleeping at the time, or was he scheming? Well, Peter Szekres was the son of the famous George Szekres of the school Szekres. Coordinates and diagram. The father seems to have taught his son GR. Newton plagiarized by stealing the work of Robert Hooke on light, and then they're adding on it, and on gravitation and adding on it, and of Leibniz on calculus. Did the father not teach his son not to steal ideas, plagiarize, but work things out for himself? We perhaps don't bother about the difference so much. We lionize A.Q. Khan, who also his fame is based on his theft. Using Penrose's idea of apparently unequal strengths due to a change of frame, treating it as a Doppler shift, we were able to identify the frequency component of the strength. Solving the nonlinear wave equation of GR, we could identify a source for the wave by the pseudotensor. However, we only obtained how the amplitude term varies over space and time, but something was still missing. The pseudotensor should have units of energy, and only then can it give the strength of the source. Thus, tau mu nu must be given by tau mu nu equal to S times f of uv times the flat metric tensor. Then the two waves would have two constants, S2 and S3, and the interaction region would have the strength S equal to the square root of the product, the geometric mean. The colliding plane wave solution after collision is then this. That gives the wave operator acting on the perturbation and gives the result proportional to the Minkowski metric, but this complicated function relating them. So I come to the epilogue. A question has been asked about the significance of the solution for actual observations of gravitational waves and its relevance if it yields no observable results. Now, I'd like to stress here, the problem is no exact solutions could ever have been observed. The short shield can't, because they use symmetries to solve the highly nonlinear differential equations. And this is, because of those symmetries, you've got an idealized situation. In particular, PS or KP waves could not be produced by any astrophysical process. The Einstein-Rosen waves could not be produced by any astrophysical process. There are no cylindrical sources of gravitational waves. That symmetry just isn't there. So this then says, well, what's the point of all of that? Then exploding supernova will be approximately point-like and will give an approximately plane wave if seen from sufficiently far away. However, we are still not likely to see two nearly plane gravitational waves collide unless the geometry and timing is just right. The question of relevance is best illustrated by a soliton, which is an exact solution of a nonlinear ODE that cannot be transformed to linear form. A wave packet looks like it, but it yields a mode analysis, and the individual modes can dissipate and disperse. The soliton maintains its form while passing through another without scattering. There's an enormous physical difference. The use of the exact solution is not to make precise predictions for experimental or observation testing. It is to provide points of principle, as John Wheeler used to say, to obtain a deeper insight into the phenomenon under investigation. By using the exact solution in its generalized form, we were able to see that for gravitational waves, a non-linear superposition principle can hold, allowing for a wave pattern. Such a solution should be looked for. There's a further difference for gravitational waves, as the field is not a scalar or a vector, but a tensor. How well could distinct modes, if such exist, allow for the cross terms of the tensor modes? Many questions of principle will arise, and some of them will lead to testable predictions. That is what the use of the exact solutions is, to pose and answer questions not thought of before and find answers leading to a deeper understanding. Thank you.
Thank you very much.
Yeah, now any questions?
Right, so do we have any questions?
I will have a problem of being able to answer because I won't hear well enough. So if people could write anything on chat, I will read it and try to respond.
That should be fine. I mean, anybody, do you have a question?
They understood everything.
Wow, it was very clear to the students. Right. This thing about this last bit that you talked about, the importance of looking for solutions of this type, I did not get that particular point. Could you elaborate that perhaps a bit?
I'm not sure that I've heard right, because I prefer the thing written, but if you're saying about the Newton comment I made in passing,
No,
if I
no,
can
I'm not talking about that. I'm talking about this last. If you could just go to towards the end of your presentation, towards the last slide or two.
I'd find it much easier. अभी मुझे पता नहीं लग रहा if it's other than I understood first, and I'm all at sea. Can we see it on the chat? I'll just read the chat and see a quick little thing that I'll to put it together and make sense of it. It is one, if you could just
Yes, I'm doing that.
could you go to your second last slide? Okay. I will just do that. And that will be second last slide is here. And I'll take this here. Yes. So now on the second last slide.
I just wanted a further clarification of what you're trying to say here. I didn't quite get the point.
Again, if it would be written, it was important to look for solutions of this type. Didn't quite see what the point you were trying to make here. Could you please elaborate? Yeah, well, what I'm saying is we, with the exact solution, are only getting points of principle, not necessarily a falsifiable prediction which we'll then test. Now, by using the exact solution in its generalized form, we were able to see that for gravitational waves, a nonlinear superposition principle can hold. Now, I perhaps need to explain what the nonlinear superposition principle is. What you have is that there's in the theory of Lie symmetry analysis, you find you can transform variables so that what looks like a nonlinear equation can be converted to something that looks like a linear equation in other variables. So you do that, and then where it looks linear, I can take a superposition of solutions. Now I can change the variables back. And when I change them back, I've got a nonlinear superposition principle, because then they all get jumbled together, and those are the ones that will come out. So I say that one could try to see if this could be converted to linear form, not by an approximation as the exact solution, change variables, and if it can be converted to a linear equation, and then you do the superposition, take it back, and now it will be, the solution will be a nonlinear combination, which will nevertheless do that. That's essentially the soliton type idea. And that will be what we'll be looking for. So I say that is what we should look for.
Right. I just put in a follow-up.
Well, I don't offhand. I'd say what would have to be done is to take the equation that we're trying to solve with its very high symmetry and convert it to use the standard Lie symmetry analysis methods to convert that into a linear system of equations, and then use the usual superposition principle for the linear solution. Now, reverse, do the inverse transformation, and you will get the nonlinear superposition. I don't have one at present, but I certainly know that in principle it is possible that such will exist.
Maybe we can ask one of Khan's students.
Sorry, again, can it be written? No, that's a joke. Khan never had any students who were anything like, they were totally incompetent. Khan himself didn't know how to solve anything anyhow. He just wrote down solution. He's pure intuitive.
That's
So I
remarkable.
don't know. But no, the idea of asking one of his students is what I find very funny, because he never had any. Well, he had an
Okay.
MS student the thesis was hopeless, totally hopeless, and I had to reject it. And that was the one and only student he ever got.
Okay, Professor, thank you very much. I think we are all out of questions unless Moise wants to ask something.
I have a sociological question since he brought some of those points up.
Okay, go ahead. I'll type it down.
So
we have one more question. I'm gonna type.
You taught him how to write it down.
I'm gonna write it down.
What Khan had done was, I think, to pray, and then he wrote down the solution.
Prayers are answered.
I think that's what he did. If I remember right, he had prayed, and then later on, when it came
One of
down
his
to
students that he mentioned
wrote
in
down the
book
solution.
has led to the destruction of general relativity in Pakistan. Any comments on that?
Well, I don't know that they're answered. Penrose has a different explanation. He says you're sufficiently concerned, then you're
This
thinking
is
about
for
it,
coffee
and
wala
that's
sir.
where the intuition
I mean, he
comes
made
in.
sociological
Yes,
remarks.
the quantum
I have a right to
wave
ask.
function